Okay, good morning everyone. So in today's lecture I am going to continue my discussion on the analysis of second variation of the functional, namely given an extremal y of the functional, can we determine the nature of the extremal. So this is the discussion on second variation continued. So please recall that in my last lecture we ended our lecture on the introduction to the Legendre condition. So recall the Legendre condition. That if I am given y being an extremal, so if y is an extremal, then y is a minimum implies that, so y is an extremal of j, which is given by integral of f with the fixed boundary points, and y being minimum leads to the condition that the second derivative of f with respect to y prime is non-negative, right. We saw that this was a good starting point to look at the nature of the extrema, but we also saw starting this lecture we will also see that this is not a complete condition, and hence later on we will develop a complete condition to determine the nature of the extremal. Okay, so let us continue our discussion on the Legendre condition. So the first example that I have is, let us look at this. So consider this fixed point problem where I have to determine the nature of the extremal. So I am given the functional of the form integral from 0 to L y prime square minus y square dx, and further I am given that I am given the boundary condition as follows. So the boundary conditions are y of 0 is equal to y of L is equal to 0, and further I am also given that L is greater than pi. Okay, we will see why this condition is needed. Okay, so if we were to look at the second variation, so if we were to look at the second variation, the second variation involved this following quantity. So it is eta prime square f of y prime plus 2 eta prime f of y prime plus eta square f of y, and this is integrated with respect to dx from x0 to x1. So once we plug in all these partial derivatives, I am going to get that this is also equal to integral of eta prime square minus eta square dx from x0 to x1, and I see that let us in particular I just want to mention that all these partial derivatives are as follows. So this is 2, so this is certainly bigger than 0, and this is 0 just taking the various partial derivatives, and this is minus 2. So that is how we get, so this is 2 times the following quantity. Now suppose I take my eta of x to be sin pi x by L. Now the reason I have taken this sort of a function, note that eta at 0 and eta at L, they vanish. So this is a good choice for our perturbation function, and this means that, so this is j of eta comma y. So this means that for this particular eta star, let's call this as eta star, my second variation of j at eta star comma y turns out to be, I will just plug in the values, I get that this is integral 0 to L pi by L whole square cos square pi x by L minus sin square pi x by L. I see that this is also equal to, once I integrate, this turns out to be 1 by 4 pi square minus L square. Now, notice that we had chosen L to be bigger than pi. For this condition, this will be strictly less than 0. So, the functional, the second variation of the functional is negative, but my second derivative with respect to y prime of the integrand is 2, which is positive. So, certainly the Legendre condition holds, but we are getting the second variation to be negative definite. Now, it turns out that one of the extremals, so note that y equal to 0, which is an extremal, or the solution to the Euler-Lagrange, this does not give the minimum, right. So, this is the implication of the non-obedience of the Legendre, the fallout of the Legendre condition here, which means that although the Legendre condition holds, we are getting the second variation negative, but the Legendre condition holds, and the implication being that we have one solution to the Euler-Lagrange which is not the minimum, right. So, the moral here is that Legendre condition is mainly a point-wise restriction. It is not a restriction which is global in character, right, or which holds for all points x in the entire interval under consideration. So, we are now going to derive a result which is global in character, but which also utilizes the advantage or the usefulness of Legendre condition. Okay. So, that condition that we are after is the so called Jacobi necessary condition. The Jacobi necessary condition. So, as I just said, so throughout our discussion I am going to only talk about deriving the minima from the extrema. Results are derived for minima. This is without loss of generality. The similar set of arguments will hold for maxima with the signs reversed. Okay. So, the Legendre condition, as I just said, is a point-wise restriction. The Legendre condition is a point-wise restriction. The Legendre condition is a point-wise restriction. We saw that depending on the values of x attained from the interval, the second derivative of f with respect to y prime will either be positive or negative, right. And even if it is positive, does not guarantee that we are going to get positive definite second variation, right. So, Legendre condition is definitely not the complete solution. So, we are going to look at, so we need necessary as well as sufficient conditions which is global in character, which means that the condition should hold for all x in the interval from x0 to x1, the interval under consideration, right. So, the goal is as follows. So this is what we need. So, we are after a global necessary and sufficient condition, and the starting point is our Morse lemma, namely we are going to appeal to the Morse zero saddle extended to the infinite dimensional case, right. So, we have looked at the Morse lemma for the finite dimensional case. So, the goal, to achieve this goal, we are going to achieve our goal, we are going to appeal to the Morse zero saddle. We are going to achieve our goal via Morse zero saddle case, which is for the infinite dimensional function space. That is, we are going to, by appealing to Morse zero saddle case, we are going to convert our second variation of J into a following form, we are going to change our del square j of eta comma y equal to a form which is integral from x naught to x1 f of y prime gamma square dx, right, where gamma is a real valued function, which means that the sign of the second variation will now be completely determined by the sign of the second derivative of f with respect to y prime, provided we are able to reduce to this form that I have shown, right. So, let me call this form 1, right. So, that is our goal. So, goal to achieve, right. So, goal to achieve. Okay. So, then also another property of gamma that we need is that gamma, of course, gamma is a real valued function. So, it is a function of x, eta and y being our extremal. So, gamma is a function of these. We seek gamma real and identically 0, real and identically 0. We seek gamma real and identically 0 only if eta is 0 in the interval from x0 to x1, right. So, which means that the sign, so this well, if we are able to find such a gamma which is real valued and vanishes for the case when eta vanishes, then the sign, we are guaranteeing that the sign of the second variation depends completely on the sign of the second derivative f y prime, right. Okay. So, let us now look at what is our second variation. So, this is from our previous lecture. So, our second variation del square j is integral from x0 to x1 eta square of f of y minus d dx of f of y prime plus eta prime square f of y prime and this is integrated with respect to x. Now, let me call this expression as b. So, then my second variation is as follows. So, this is integral from x0 to x1 eta prime square f y prime plus b times eta square. This is integrated with respect to x. Okay. So, let me call this form of the second variation by 2. Let me denote it by 2, and now I am going to do a small trick. Notice the following. Note that eta vanishes at the boundary, right. So, eta is a perturbation. So, which means that for this observation implies for any smooth function, all I need is the continuity of the function, and later on we will also see we also need the differentiability of the function, at least first order differentiable. So, for any smooth function, it implies that the condition for any smooth function, the condition 2 is not changed if my integrand to the functional integrand is modified as follows. So, instead of the original integrand, so let us look at the original integrand. My original integrand is f of y prime eta square plus b of eta. So, this one was f of y prime eta prime square, and this is b of eta square. Now, this was my original integrand into, and then if I add this quantity w eta square whole prime, note that the integral of this quantity w eta square whole prime dx is the evaluation of this quantity from x0 to x1, and due to this boundary condition, this vanishes, right. So, this the integrand in our 2 is identically equal to this new integrand, right. So, this was our original integrand which we have highlighted, and the new integrand includes this additional quantity which is not going to change our integral, right. So, we want that this is also equal to the following final quantities. So, this is what we want, right. So, this is what we want. Let me call this expression as 3, right. So, what we want is, we want to find, so the idea is we have to find omega such that 3 holds for some gamma, some function, some real valued function gamma, right. So, this is our goal. Now, notice that so what have we got? So, so from 3 what we get is the following. We can take this common out, this quantity f y prime. So, f y prime taken common out, I get the quantities eta prime square plus b plus omega eta square. So, I can omega prime divided by f of y prime. Note that the third quantity can be differentiated using product rule. The first term is already absorbed here. The other term is plus 2 omega by f y prime eta prime, right. So, this is set equal to, so note that this is our expression 3, right. Okay. So, expression 3 is as follows. We see that, let me call this as 4. So, I call this as expression 4. Now, so all we need to do is, this quantity inside the bracket that we have to reduce it into a perfect square of some function. So, that is possible if the following holds. So, suppose my w satisfies the ODE given by w square equals f y prime b plus w, right. If that is the case, I see that this is for all x in the interval x0 to x1. So, suppose this is true, then I can reduce. So, then 4 is, so let me call this ODE by 5. So, if 5 holds, then 4 is identically equal to f y prime times eta prime plus omega eta divided by f y prime whole square, right. So, my obvious choice for gamma in that case will be this quantity inside the bracket. So, if I were to find a w such that w satisfies this ordinary differential equation, which is a first order non-linear equation, then I am guaranteed that I can get a gamma such that I can reduce the quantity inside the bracket, given by 4 into a perfect square, right. And on top of that, suppose we have the strengthened Legendre condition. Suppose further the strengthened Legendre condition holds, right. That is that is f of y prime is strictly greater than 0, right. So, then it implies that del square j comes out to be strictly positive, right, strictly positive right away. So, the conclusion is the following: for our positive definiteness, of the second variation of j, I need that there is a solution to 5. For the positive definiteness of j, I need a solution to 5. Okay. Now, let us also look at, so if that is the case, let me also choose my function gamma to be the quantity that I found out inside the bracket. So, gamma is eta prime plus omega by f y prime eta. So, we choose this gamma, right. So, if we do that, let me call this 6. Now, so it turns out that gamma is 0. So, when is gamma 0? When eta is going to satisfy the ODE whose expression is given by 6, right. So, gamma is 0 when eta plus omega f y prime eta, this is 0. Now, further we know that eta, the function eta is smooth, right, which means that it contains all its derivatives, at least the first derivative as well as the function itself is continuous, and also that so this is all given. So, also that eta vanishes at the boundary, right, eta vanishes at the boundary, which means that this is a first order ODE. Then by Picard's theorem, a standard theorem in our theory to first order linear ODE systems, by Picard's existence theorem, there exists a solution eta. Well, in fact, now there exists a unique solution because I have that both the function as well as its derivative are continuous. So, there exists a unique solution eta satisfying the boundary condition which is given by this bracketed quantity, right. Now, I can see that one solution to this ODE given by the expression in 6 is eta equal to 0, right. So, since eta is a unique solution, then eta is identically 0 is our unique solution that we are after, which satisfies the boundary condition as well, right. So, which means the following: the conclusion here is that the grand conclusion out of this small discussion is that gamma equal to 0 if and only if eta is 0, right. So, gamma is 0, no, that is only one way. So, gamma is 0 only if eta is 0, right, and gamma we know that is a real valued function. Okay. So, then let me summarize our discussion in the form of a small result. Let me call this as a lemma. So, the result is as follows, right. The result is, so let my function f be a smooth function, of x, y prime, and let my function y be a smooth extremal, right. Let my function y be a smooth extremal for my functional j given by integral from x0 to x1 f of x y prime dx, such that my strengthened Legendre condition holds. Then this is for all points on the interval x0 to x1. Then if there exists, if I can find a solution to my ODE that I had just mentioned, satisfying the solution to the ODE 5. So, if there exists a solution to ODE 5, that I have mentioned the slide before on the entire interval, it implies that in this case my second variation will be positive, is positive definite, right. So, all I have to do is to find the solution to the ODE that we had assumed, right, and provided that the solution exists, right. So, let us now focus on the solution to the ODE. So, what is the ODE again? So, let me write down. So, the ODE 5 is omega square is equal to f y prime b plus omega prime. So, this is my ODE. This is for all x in the interval x naught to x1. Notice that this ODE is the famous, it is in the form of a famous Riccati equation, the Riccati equation, and secondly this is also a first order ODE, first order non-linear ODE because of the presence of this omega square terms. So, the first step that we will do is we are going to change it into a linear ODE in order to satisfactorily find the solution to it, right. So, we use substitute omega, which is equal to u prime by u times f y prime, right. So, in this case my 5 is identical to the following. My expression 5 is d dx times f y prime u prime minus b of u is equal to 0, where my quantity b is f of y minus the total derivative, the ordinary derivative with respect to x of f y prime y prime, right. So, this is my b. Okay. So, note that this is a second order linear differential equation, and also known as the Jacobi accessory equation, right. So, this is certainly a step forward in solution to the ODE because this is slightly easier to solve. Okay. So, then let me call this ODE expression. Let us see what equation number we have gone so far. We have until 6. So, let me call this ODE expression is ODE by 7, right. This is also known as the famous Jacobi accessory equation, or I will in short term note it as JAE. So, from now on JAE will denote the equation 7 or the Jacobi accessory equation. Okay. So, some of the properties of JAE, let me mention some of the properties. So, the first property is that the smoothness of f implies that since f is smooth, the second derivative of f with respect to y prime and b, these are also smooth, right. And further we have also assumed that the strengthened Legendre condition holds, which means that the coefficient of u prime in this derivative is non-zero, which means that the solution to this equation will be non-singular, or the problem is non-singular, there is a solution to this problem, right. So, my strengthened Legendre condition implies problem is non-singular, right. And suppose we are given an initial value, suppose we are given an initial condition to this equation, then my continuity of the function f will guarantee via Picard's theorem that there is a unique solution in a neighborhood around that initial point. So, what I just said is the following: given initial values u naught, let us say, which is u of x naught, and u naught prime, which is u prime at x naught, given initial values, my Picard's theorem will guarantee, my Picard's theorem guarantees, uniqueness of solution, right. Okay. In a small neighborhood, right, neighborhood of x naught. Okay. Okay. So, then moreover, it turns out that since the solution is smooth, I can extend this uniqueness in a small neighborhood around this point x naught to the entire interval x naught to x1, right. So, the uniqueness of the solution, solution to our equation 7 can be extended in the entire interval x naught to x1 via the standard arguments of the continuity as well as the continuous differentiability of the solution. The solution that we are solving will be continuous because the coefficients of the ODE are continuously differentiable. Okay. So, then finally, another property is, note that the Jacobi accessory equation is a second order linear differential equation, which means that there will be two linearly independent solutions, or any linear combination of the two linearly independent solution will also be a solution to this equation, right. So, we get a family of solutions. So, suppose for any two linearly independent solutions u1, u2, I see that the solution u, which is alpha 1 u1 plus alpha 2 u2, is a linearly independent solution of the problem. Okay. So, that is it in terms of the solution to the Jacobi accessory equation.